Hello, on the previous video, what we have done is we break down the forces, uh, axial force, shearing force, and moments in the X, Y, and Z component. That's what we've done. Okay, so we're going to use all this data over here that we've calculated. To firstly, we're going to calculate stresses, combined stresses at element A and then element B. Okay, and the objective is to calculate the maximum principal stress and shearing stress at element A and B. So now let's look at element A. Okay, let's focus on element A first. Okay, so we're going to focus on element A, and we did have our transformation where we did define that this is X, and then this is our Y, and then this is our Z. Okay, so let's sketch out element X. Okay, so this is element X. So this is how element X should look like when we sketch it. Sorry, element A, not element X. I do apologize. So this is element A. Okay, so based on this orientation, element A. Okay, so this is element A. So what we're going to find we want to find what is our stress in the X direction, if there's stress in the X direction, stress in the Z direction. We're going to find is there any stress in the Y direction. And over here, this plane, the shear, so we want to find out is there any shear on the X plane, Z direction, and this is equal to shear in the Z plane, okay, X direction. So that's what we would like to inquire now. Okay, so let's look at stress X. Okay, so stress Z is equal to P over A. But before I carry on, so these are the values of the beam of the cross section W 200 by 41.7. Okay, so you have the area IXX, IYY, thickness of the flange, thickness of the web, width of the flange, and the depth is equal to 205 meters. Okay, so we calculate stress Z. So we know that minus PZ over A. So Y minus because it's on compression. Then we have, do apologize, this is stress X, Z at element A. Okay, and then we have MX over IXX multiplied by Y. Then we have MY over IYY multiplied by Z. Okay, so if you look at MX, so you look at previous slide, okay, MX. So moment about X, right, at element A, right, so this is moment about X over here. At element A, you induce a tension, so it's going to be plus. And then element Y, you can see from here, moment Y will induce a compression on element A, which you have written down here. So this will be equal to minus. That's why writing whether it's tensile compression is so important. Okay, so we have this will be equal to minus 100 times 10 to the power 3 divided by area. Area we're given over here is 53320 times 10 to the power minus 6 plus by moment in the x direction. So you go over, you look at moment x, which is equal to 22750 divided by IXX. So IXX is 40.8 times 10 to the power minus 6. Then multiply by y. So this is where your element A is. Okay, so this is where your element A is. So y direction is on this direction over here. Okay, so this is our y direction. Okay, from the neutral axis, so it's 0.205 divided by 2. Okay, so that's done. And then the next one is minus by moment about y, so 9600 divided by IYY, so 9.03 times 10 to the power minus 6. Then multiply by z. Okay, not z, by x distance. So this x distance is to the element. So this is what we mean by x distance. So we are aware that from this question, A is 75 off. Okay, so the width is 0.166 divided by 2 minus by 75 times 10 to the power minus 3. So this is our stress at point A. So 100. So this is equal to minus 18.797 times 10 to the power minus 6 plus by 57.154 times 10 to the power 6 and that was the last one is 8.505 10 to the power 6, so 18.7, so minus 18.797 minus by 8.505, so it's equal to 29 positive in tension, 29.852 times 10 to the power of positive 6, Pascal. So we found our stress Z at point A. Okay, and we realize that stress X and stress Y are equal to 0. There's no normal stress acting there. So now we are going to find the shear. So we're going to find a shear X. We're going to find a shear on Z X direction induced by or generated by Vx. Okay, we're going to apply, and we're going to use thin wall analysis. Okay, so so this is our cross section again. I'm going to paste it here. So we know that we have a Vx contributing 16,000 Newton. So when we sketch the Q, okay, the shear flow, it'll look like that. Shorter the arrow. Okay, you do this. And then in the between, it will go in, one will go in here, one will go in here. So these two will cancel out. Action equal reaction, they will cancel out. So there's nothing to calculate there. Okay. So we're going to use, we're going to find, so looking at the Vx direction. Now this part is a bit tricky, okay, you have to be careful. So we know that this is your element A. We know over there that's our element A. So we are aware that the Vx intersect the y-axis. Okay, so we realize that Vx intercept the y-axis perpendicularly. Okay, perpendicularly. I don't think that's such a word, but anyway. So we know that this over here is a shear, right? Because shear Zx is equal to Vx because it intersects the y-axis perpendicularly. Iyy, first moment of area about the y-axis. Okay, divided by thickness, right? So we're going to take the first moment. So we know that Vx. So what do we know? Vx is equal to 16,000. This is what we know. Iyy will be equal to the yy. I think we wrote down to be 9.03 meter to the power 4. Thickness will be equal to what we have as Tf. So Tf is 7.24 times 10 to the power minus 6 minus 3 meters, sorry. So we are going to analyze Q. So remember the rules that we have. So Q is based on this area, right? Because the analysis is in this direction. The 4 rules that I taught earlier. Okay, so that is the area of interest. Let me, I do apologize for this. So this is the area. So this is our analysis direction. And this is the area that we are interested in. Okay, so this is the area we're interested in. Okay, this small region up to where this line stops. Okay, so now we're going to do QY. So first moment of area about the y-axis, so equal to A x bar. So about this axis, right? So if this axis, I'm going to calculate. So if this axis is fixed, right? So this axis is the lock-in axis. This direction over here, from here to here, is going to be your x bar. Okay. So now we're going to calculate our area. So it's equal to the width So the width over here is the width that we have is TF. So TF, sorry, I think I got my, it's 11.8. okay, sorry. So this is 11.8 because we are looking at the flange. So area, so the width will be 11.8 times 10 to the power minus 3. The depth is equal to 0.075. And the X bar will be equal to 166 divided by 2, or 0.166. Right? Why is 0.166 is because we are taking BF, 0.166 minus by 0.075 divided by 2. Okay. So why is that? So if this is the neutral axis and this is the section of concern, we know the distance from in the shaded region, this distance is equal to 0.075 divided by 2, right? And then the distance from here to here is equal to 0.166 divided by 2. So what we have just identified is this is our X bar, which is what we did over here. Okay, so that's why the calculation is that way. So when you add this up, or when you calculate this, times by 0.075 times 11.8 power minus 3. So it's equal to 40.2675 times 10 to the power minus 6 meter, and this is going to be cube. Okay, so from here we can calculate our shear X, our shear ZX, which is also equal to our shear XZ. So this will be equal to 16 times 10 to the power 3. The area Q bar is 40.2675 times 10 to the power minus 6 divided by I, YY 9.03 times 10 to the power minus 6, and the thickness over here is 11.8 times 10 to the power minus 3. So shear stress will be equal to 6.0465 times 10 to the power minus 6, so 10 to the power 6 Pascal. Okay, so it's going towards the left hand side because look at the arrow down here. Alright, the shear is going down in this direction. Okay, for that section. Okay, so then later, the next video, I'll show you how to find the shear stress induced by Vx.